Well, we're about halfway through our class, so let's take a second to review the labs that we've done so far, the components that we've used, and then in the next video we'll see how to build an actual circuit that has to do with biomedical engineering. We'll be building something like a pulse oximeter. So before we can build that kind of cool, interesting circuit, let's just take a look at where we've been. We've seen resistors. There's our schematic for a resistor. It's got a resistance R in the units of ohms. We know that there's voltage across components. There's current through components. We don't have voltage through something. We don't have current across something. It's always voltage across and current through. And for resistors, we have Ohm's law, V equals IR. Those are fun. Let's see if I can take out a resistor. Here's a 1/4 watt resistor. This is brown, black, yellow, gold. So this is a 100K resistor. The gold means that this is plus or minus 5% over its temperature range. I find that they're a lot better than that. And a 1/4 watt means that it can dissipate a 1/4 watt before it smokes. And the power in any component is the current through it times the voltage across it, and that has the units of watts. And you can solve for a resistor to say V equals I squared R, or P equals I squared R, or P equals V squared over R using Ohm's law. We also have this special case of a resistor called a potentiometer. We just call it a pot. And from the top down, it's got 3 legs, and it's got a knob that if we turn the knob, we are changing the ratio of how much resistance there is from A to W and W to B. And for your particular potentiometer, from A to B is a 10K potentiometer. And we typically use resistors and potentiometers to build voltage dividers. Okay, so a voltage divider, we typically have a V in that goes to 2 resistors in series, and V out. And we can solve for V out in terms of V in and our resistors. By combining these two in series, solving for the current, and then knowing that the current is the same through both LEDs, that the V out is the same thing as the voltage across R2. So V out is I times R2, and okay, so we solve that way. We also, instead of fixing our resistors, we can do something like plus 5 volts to minus 5 volts on our potentiometer. And this voltage will range between plus 5 and minus 5, depending on the angle of the potentiometer. And normally we would label these its value just so we don't forget 10K. Very occasionally, we do something weird with our potentiometer where we use it as a variable resistor. So we might put 5 volts up here and, I don't know, do resistor to ground over here. Now we've got some V out. Now as you turn the knob, you can make this resistor as high as 10K and as low as 0 to make some kind of like variable adjustable potentiometer that you could have probably done here, but we did this way. In this case, we just don't hook up that leg. So this is a variable resistor configuration for a potentiometer. Okay, we use voltage dividers to make voltages smaller. The next thing we looked at were op amps. We started out with op amp as comparator. And so we have let's call it 1 and V2 go into the 2 inputs of our op amp, V plus and V minus, and V out is going to be big G times V, let's see, in this case the way I drew it, V1 minus V2, where big G should be infinite. So V out will go either to plus 5 or minus 5, depending on which one is even just a little bit bigger. Okay, we don't use comparators a whole lot unless we're kind of at the end of a circuit and we need to make a decision which voltage is bigger. Usually we use our op amps with negative feedback. So these would just be regular amplifiers. And we have a bunch of standard ones. We have the non-inverting. We have the inverting. We have the summing. We have our differential. And we have our buffer. Okay, the non-inverting amplifier, V in goes to the positive side of the op amp. V out is the sum of the two resistors, or the one that goes to the ground, V in. So we call this our gain. V out is always the gain little g times V in. So in this case, little g is always bigger than 1 and always positive. Our inverting style op amp is negative. The feedback resistor divided by the input resistor. Our summing amplifier might have several V ins, so I'll draw it with 2. Each gets its own resistor, and other than that, it looks a lot like the inverting op amp. And so we have V out is equal to, and the summing is also happens to be negative, negative RG times V1 over R1 plus V2 over R2, and so on. Okay, our differential is how you subtract two voltages. Let's call it V1 and V2. Getting very messy here. Okay, V out. If all of the resistors are equal, we can say it's going to be V2 minus V1. If the resistors are all different, we get a much more complicated equation. And finally, the buffer. V in goes to the positive input of the op amp, the negative goes to the output, and the gain is 1. So this essentially doesn't seem to do anything. V out is equal to V in. Why do we have it? Well, when we take a look at our voltage divider, there's only so much current that leaves V in to go towards ground. If we steal some of the current towards V out, this voltage is going to dip. So it's our job to make sure when we take the voltage output of a voltage divider, or really any circuit because it has an equivalent resistance to it, we don't take too much of that current so this voltage doesn't dip. So we either need to make sure that the current that leaves is 10 times less than the current that continues this way, or we can have the buffer, and in the buffer no current will leave this circuit and the voltage will be completely preserved. So the buffer is here to protect the input from wherever the voltage is going on the output. Along the way with these amplifiers, we used a light sensor, specifically a phototransistor. We schematically draw it like a transistor, which we haven't covered yet. We draw a little circle around it, and there's the light that comes in. And the phototransistor acts like a little switch, so it allows current to flow when light hits it. So we will turn that current into a voltage, which is, so V out is I times R. I is proportional to light. So V out is now proportional to the amount of light that comes out. And we're usually in the order of 10K, 100K, a million. Pretty big resistors because the current is typically small. We also used some LEDs. Here's an LED. An LED is a directional device where when current goes through it, light comes out. So we typically put it with a resistor, maybe 100 ohms. The smaller the resistor, the brighter the LED will be. And V in here has to be bigger than probably 1.6 volts because diodes have some magic amount of voltage that if you don't pass that threshold, no current will flow in the direction of the arrow. So for an LED, it's something like 1.6. And then we also have diodes. Here's a picture of a little red signal diode. and we draw the schematic like this. Current can only flow in the direction of the arrow, and the voltage here usually needs to have a magic threshold of like 0.6, bigger than this voltage, before current will flow. And for an LED, the long leg is the positive leg. For a diode, the side with the line is the negative line. The negative side. We can also talk about the pinout for the op amp. We're using the 272. Has a little dot in the top left. 1, 4, 5, 8. Those are the pins. 4 is the negative 5 volt. 8 is the plus 5 volt. And it's out minus plus, out minus plus. Pin 5 is that's not 5 volts, that's pin 5, and it happens to be the plus of that op amp. Okay, well, that's my quick review of all of the circuits that we've built so far and the components that were in them. So the next thing we're going to do is start building more functional circuits using these things that we've built so far to see some interesting biomedical signals.